All right, so now we get to part 3, which is what's called an initial value problem. So in this case, this is where given information lets you solve for that constant, that plus C piece that we were having to keep writing. So let's look at the first example. Right, it tells you that the derivative is x squared plus secant of x tangent of x plus sine x. And then it tells you that y of 0 is equal to 4. So we're going to use this bit of information later. Right, so we're going to take the antiderivative. The antiderivative of x squared is x cubed over 3. Right, this is all one term. Don't try to split it up. If you look at your antiderivative rules, the antiderivative of secant of x tangent of x is secant of x plus c. Right, so this second piece would be just secant of x. And then the antiderivative of sine of x is negative cosine of x, and plus a constant. Right, you can check your work. Right, the derivative of x cubed over 3 would be 3x squared over 3. Right, you bring the exponent down, decrease the power by 1. The derivative of secant of x is secant of x tangent of x. The derivative of negative cosine is a negative sine x. The derivative of constant is 0. This is x squared secant of x tangent of x plus sine x, which does match the original function, right? X squared secant squared of x, secant of x tangent of x, and sine x. So we know that this is the correct antiderivative. Now let's use this given information. This tells me that when I plug in 0, I'm going to get a y value of 4. Right? So this tells me that we get 4 is equal to 0 cubed over 3 plus secant of 0 minus cosine of 0 plus a constant. Okay, so I plug 0 in, we're breaking an x. Right. 0 to the third divided by 3 is 0. Secant of 0 is 1. Cosine of 0 is negative 1. Right, so that means that 4 is equal to c. So that means that this function, I can actually change this. Right, so this function is now not dependent on a random constant. This extra information tells me that the constant is equal to 4. Okay. Right. When you get y of 0, it's not always your constant. Right? It happens a lot, but it's not guaranteed. Right? Y of 0 happens before, which happens to also be the constant. Right. So let's look at the second example. Like this. Okay. Second example we're given is that y prime of x is 5 over x plus the cube root of x squared. And we're given y1 is 5. All right. So before I start hacking away the antiderivative, I'm going to rewrite this as 5 times 1 over x, and this is x to the 2/3 power. Okay. So odd radical cube root 1/3 power. Right. When you take the antiderivative, you get y of x is 5 times the absolute value of x, plus x to the 2/3 plus 3 is 5/3 over 5/3 plus a constant. So this is the ln rule here. The antiderivative of 1 over x is ln of x. And then this is the power rule. You take this exponent, you increase by 1, 2/3, 3/3, 5/3, and divide by the exponent. Oops. All right, so I'm going to rewrite this. All right, I just keep changing flip, 5/3, reciprocal, it becomes a 3/5. And now we're going to use this information, right? So it tells me then y is equal to 5. All right, when x is 1. So we're going to get a y value of 5. All right. So if you were to put this in your calculator, ln of 1 is equal to 0. So this part is entirely 0. Right. 1 to any power is equal to 1. Right. So you get 5 is equal to 3/5 plus c. Multiply with 5, you get a 5 equals 3 plus 5c. Right. But I didn't multiply everything by 5. Just to get rid of the denominator. 5 times 5 is 5, 3 times 5 is 3, 5 times c is 5c. 23 equals 2 plus 5c, so 22 over 5 will be my constant. So my original function was 5 ln absolute value. Don't forget the absolute value. And then plus 22 over 4. 22 over 5. Right, so this is my function. All right. One more example here. Right. This one is a little messier because it's actually given the second derivative. E to the x, 2x plus cos x. All right. And it tells you the y prime of 0 is 4 and y of 0 is 0. All right. So notice this is the second derivative. If you take the antiderivative of the second derivative, you end up with the first derivative. If you do it one more time, then you get the original function. Just like when you take the derivative of the original function first, take the derivative of the second, first derivative, you get the second. So there's two different antiderivative steps that we're going to do. And we're going to do it right now. Right. So I take the antiderivative of e to the x. It will be e to the x. Antiderivative of 2x would be 2x squared over 2. The antiderivative of cosine is sine. Then we're going to have a constant. So I'm going to call this constant C1. Okay. Remember that the antiderivative of integrals, antiderivative of cosine is a positive sign because the derivative of sine is cosine. Right? The derivative of sine is cosine. Okay. So now we're going to use this information. I'm going to plug 4 in for y, e to the 0, this is x squared. All right, so as promised, right, that constant is not always this number here. E to the 0 is 1. All right, so that means that 3 is equal to c. All right, this is 1, there's zeros. So that means the first derivative is now something I know. Right? This is the first derivative with this value plugged in. Now we're going to take another antiderivative. Right. If we do that, we're going to get the original function y of x. Right? Antiderivative to the x cubed over 3. The derivative of cosine is negative sine, so negative cosine is the antiderivative of sine. Plus 3x plus, I'm going to call this 2 here. All right, I'm going to show you this now for the running out of space. Okay, so now we're going to plug in this bit right here. All right, so 3 equals e to 0, 0 cubed over 3 minus cosine of 0 plus 3 times 0 plus c2. All right, e to the 0 is 1, 0 to the third, 0, cosine is a negative 1. All right, so in this case, 3 is equal to c2. All right, so that means the original function would be e to the x plus x cubed over 3 minus cos x plus 3x plus. Right, so we were given the second derivatives, we had to do antiderivative twice, and then we were given two pieces of information about the first and second derivatives, which allowed me to compute the constants that I get and take the antiderivative.